Let's
now
discuss
we
about
have to
alpha particle
investigate
decay.
that why does
In a radioactive
a
nuclei,
radioactive nucleus takes some time,
scientists
sometimes
have
a very longer time
examined
to
that
decay.
in case of
Why does
radioactivity, a
there
radioactive
exist a half-life
nucleus
at all?
emits 3 types
Why
of
does
radiation.
the
2 are particles,
all the alpha particles are
and
not coming out
these
of a parent
radiations
nucleus
are classified
instantaneously.
according
Let's have
to
a bigger
their
nucleus with
behavior
A greater than
inside
150,
an
that is,
electric field.
we are in
And
the
of
high
course inside
end
a
of
magnetic
the
field
NZ
also. I have
stability plot.
drawn here the electric field only,
And let's
for simplification.
imagine that
This is alpha particle.
alpha particle
and,
is already
actually
there,
scientists
like in the shape of a
have
bubble,
shown that
and
there
it
are
is
3
just
types of
wobbling
radiation.
inside. It is just
One is
traveling
positively
inside.
charged alpha particle.
So what
This
is
should
the
be-
potential
This should be
this
deflected
alpha particle
along the
has
negative
to
side of the
face
plate, and beta
during
should
its
be
journey
deflected along
within
the positive
nucleus
side of the plate,
and of
because
course outside the
beta is
nucleus.
negatively charged, so
This
negative
is the
positive
potential
attraction,
plot.
and alpha particles will be
We
deflected
still do
towards the
not know
negative
the
plate
exact
because
form
it
of
is
the
positively
potential, but
charged.
now we are taking the
And in case of gamma
square
ray,
well,
which
because
is
it can
having
simulate quite
energy even more
the
than
nuclear
X-ray,
potential.
and it is very
well.
fertile
Within the
too.
nuclear radius,
This
the
high
nuclear
energy
potential
electromagnetic
is
radiation
negative, that
just
is,
passes
it is
through
attractive
this
in nature.
electric field,
Outside,
as it does
is
not carry any
Coulomb
charge.
repulsion, and the
So this is
force
the
is 1
basics
by r
of
square.
alpha
So
particle
potential is
decay.
obviously 1 by r.
Alpha is nothing but the
Alpha
helium
particles
nucleus.
are having
Beta
already
is
some
the
energy, some
negatively
kinetic
charged
energy,
electron
which is denoted
coming out
as
from
Q.
the nucleus,
and
and gamma
is
is the
constant.
electromagnetic radiation, high energy
so an
electromagnetic
alpha
radiation.
particle with
In
Q
order
energy
to
is going like this.
examine the reason for
But
the
at
alpha
this
particle
portion,
decay,
when smaller equal
let's
to
again
capital
refer
R,
to the stability graph.
up to this,
This is
with a
N
certain
versus
value
Z
of R,
graph,
I
number
mean
of neutron
X here.
versus number of protons. We
That
have
is,
discussed this
when the alpha
in
particle
detail in the
is
semi-empirical
on,
mass formula video.
the radius itself, the radius is not though
This is the
very
stability
much
line,
defined
straight
as
line,
we are
and
defining
as Z
a radius
increases,
classically
the
of a
actual
circle.
experimental
In case of a circle,
value,
classically
actual
we can define
experimental
the radius very well.
manifestation
But here it's a quantum mechanical
of the
object.
behavior
The nucleus is a quantum
of this
mechanical
stability
object. So
is like this
this
curved
rim
line.
is very fuzzy.
For lower
because
Z,
there is a probability wave
These
associated
two
with,
lines merge, but
everywhere.
after a certain value of Z,
So
this
within
again
this
becomes
region where the
like a-
Coulomb potential
like a
outside
curve. This
the
curve in
nuclear
nature
radius R,
occurs.
the Coulomb potential, let's call it
And
VC,
when the
over
nuclei
here.
are
And
in
we can
these
see from this
regions,
plot that Coulomb potential is quite greater than
suppose
the
there
kinetic
is a
energy of the alpha
nucleus,
particle.
which is having
classically,
extra
how
neutron,
is it
so
possible
it is
for the
on
alpha
this
particle
side of
to
this,
overcome this Coulomb
graph,
potential
as it is
and
having
come
greater amount of
to this
neutron than the
region
protons.
3, because unless it
So first it will
gets
emit
out
neutron,
of this region
so
2,
it will come
we
down
can't-
by 1,
we are not able to detect the alpha
and then
particle.
again
So it has
its
to
proton
overcome
number
this
is
VC, the Coulomb potential
increased
in this
because
region, and it has to
neutron is
come out in
converted to
region
proton.
3 in order
That
to
is
be
the
detected.
beta decay. Weak interaction is
So now
responsible
we
for
have
this
to
interaction.
Analyze the
So neutron
nucleus
number is
quantum
decreased by
mechanically.
1, proton number is
We have
increased
time
by 1.
independent
So
Schrodinger equation.
now this
We need
nucleus
to solve this. So
is
time independent Schrodinger equation is
quite
minus h cross
near
square by twice m.
this
M is the
stability
mass
graph.
of the alpha
That
particle.
means
d2
this
psi dx
reaction
square psi is
gives
a wave
a
function
better stability for this nucleus.
plus v psi equal
Same
to
thing
e
happens for beta
and we
positive
can
decay,
rewrite this equation
where
like
a
this.
proton decays into
Here
a
the
neutron.
energy of the alpha
So a
particle
positive
is
charge
q.
decreased.
We already have mentioned there it.
I mean, it should
And
be
potential
it first
is Vc
it
here.
first go like
As we
this
can
because
see
positive charge
from the
is
plot,
decreased.
the potential is
Then
Vc here, and the energy
neutron
is
number
q.
is increased because
So if
proton
we
is
put
converted to neutron
E equal
here.
to q
So
and v
it
equal
will
to
move
Vc,
up
our equation looks like this.
by 1. So
Now
it
this
hits
quantity
or it is almost near
always
the
a
stability
negative quantity
graph.
because q
So beta
is
minus and beta plus decay
lesser
is
in
basically
this region. We call it region 2. In
to
this particular region,
achieve the
q is always lesser than Vc.
nearly
So q
region
minus Vc
of this
is
stability
always
graph
a
to
negative
achieve the
quantity,
stability, more
and
stability.
negative positive. So we call this
Here,
entire quantity
We
as
will
k
discuss
square,
beta
and
decay
k square is
in a
itself
short while,
positive
but now we
quantity.
will discuss alpha
So our
decay,
time independent
where
Schrodinger
a
equation
particular
will
nucleus
become
with z number
d2
of
psi
protons
dx
and a
square
number
equal
of
to k
proton
square
number of
psi, where k square
nucleons
is a positive
decays
quantity.
into
And the solution
these two daughter
will be
nuclei
like this.
This is parent nucleus, these two are daughter
It can't be
nuclei.
a harmonic oscillator
This
solution.
is Z minus
So
2
it is a
proton
mixture, it's a superposition
nucleus,
of
and
e to the power kx
it
and
is
e to
A
the power
minus 4 as
minus
alpha
kx
particle carries
solution.
plus 2 charge and
If
plus
we plot
4 nuclei
these two
with
solutions, it would look like
But there is a
this.
release of energy also.
this is
in
the
this reaction.
exponentially growing term e to the power plus
This
kx.
mass energy of
There
this
is an
left hand side nucleus,
exponentially
that is the
decaying
parent
term
nucleus,
e to the
is
power
greater
minus
than the
kx,
mass energy
which is
of
this
these
one.
two products.
But
And this is something
if
in
we
this, in this
uh,
reaction, greater
make
mass
the
energy
logic
becomes smaller mass energy,
that we know
which is
that
very favorable
square
to nature.
is
Nature
actually the
would
probability.
happily decay from a higher
And
energy
if we
state,
make
mass
chi
energy
square
state,
of
to a
this,
lower mass energy state in order to
so
get more
probability of
stability,
finding
because
the
nature
alpha particle
always wants to get
is
into
maximum
more stable situation. And
for a
this
very
amount
large
of mass
value of
energy is
x,
released as
because only then
energy value for this
this
reaction,
factor becomes
which is
quite
denoted
large,
as Q, which is called Q
which
value
will
of the
in
reaction.
turn makes
But the
chi
question
square
is,
more large,
do all the parent nuclei
and e to the power minus
convert
kx
to
will become
this alpha particle and energy
shorter, will
and
become
other
lesser,
nucleus also?
because if
In
x
a
increases,
certain instant, that is,
exponential
I
minus
have this
kx
particular
decreases,
radioactive nucleus,
and
and
if
within
x
fraction of
increases,
second, all the nuclei will
plus
decay,
kx increases,
and they will produce alpha
so
particles
as
and energy.
x
Let's find the
increases,
answer.
this term, the answer
will
is of course
increase-
not. Will be increased.
all
and
the
this
parent
term
nuclei
will not decay
decreased.
into the product nuclei.
So if we make
and
chi square
energy, that is into alpha
for a
particle
larger
and energy
value of x,
within a fraction
this
of
term
seconds,
will dominate.
it will take
And what
time.
does that mean?
And
That
we have
means
already
The
derived
probability
in our
of
fission
finding
video
the alpha particle is a
that
maximum
what is
at
what
the
is
other
the
side of the
factor
universe
which is
where
governing this decay,
nucleus
and
is
number of
emitting the
decays per
particle
second is
from
proportional
itself,
to n,
which is a
the
complete
number
nonsense.
of atoms or nuclei present
So
on that
we
particular
can
instant, which is
easily
quite
omit
obvious,
this
because
portion
if
of the
more
solution.
number of nuclei or atoms are present, then
we need
obviously
to keep only
decays
this
will be
portion
more
b
in
e to
number.
the power minus kx.
And we have already derived
So
this
here,
relation.
The solution for
We have
region
already
2
derived
becomes
this relation, n equal to
psi
n0 e to the
equal
power
to
minus alpha
b e to the
minus
power
lambda t, where
minus
lambda is
kx,
called
where
the
k
decay
square
constant,
equal to minus twice
which
m
governs
by
the
h
decay
cross
of the
square q
radioactive
minus
nuclei. In the fission
Now
video, we
let's
already
check,
deduced this
two
relation.
conditions. For
And
example,
we have already deduced this relation
when
in the fission video.
the energy of the alpha
The
particle,
relationship
the kinetic
between
energy
the
of alpha
half-life
particle, which is
and the
almost
decay constant,
98% of the Q.
and we
So
have
we can
already
take
plotted
as
this
Q.
fission
Right.
decay
This does not make any
graph
difference,
also,
in a
that
larger
how
scale.
the number of
So if the kinetic energy
atoms
of the
initially
alpha
present
particle is
decays
very
with
small
respect to
compared to
the time
Coulomb
in case of
barrier,
radioactive nucleus.
so this thing
Let's
becomes
come to
very
the
small.
alpha particle decay.
If
We have a
this
parent
difference
nucleus
is very small,
X, Z, A.
k square is a
Obviously,
smaller
this is
quantity,
having a very high value of A
which in
and Z,
turn makes
and
e to the power
this is
minus kx
undergoing fission reaction. We are getting
to
smaller fragments
decrease
like Y and alpha particle
in
and
a
some energy.
very
Now this Q is the
steep
kinetic energy,
fashion.
and this kinetic energy is distributed among alpha particle and the product other product nucleus, which is Y.
খুবই ছোট হয়,
If we
এই quantity,
picture
এই যে
this
difference
phenomena
টা, এটা
classically,
অনেকটা বেশি হয়ে
this is
যাবে।
the classical
তার
picture.
ফলে
Let us
k
think
e to the power
that
minus kx
this
এই quantity টা
nucleus
অনেক
X
steeply
is in the
decrease
form
করবে।
of a ball,
But if Vc is almost
and
equal to
it is
Q,
emitting
Vc যদি
alpha
Q এর
and
সঙ্গে
Y
মোটামুটিভাবে সমান
nuclei.
হয়, তাহলে এই
And
k
this is the
square এর
kinetic
value টা
energy, and
খুব
initially
বেশি
this is
হবে
at
না।
rest. This
ফলে
X nuclei is at rest.
kx যেহেতু k এর ভ্যালু
So initial momentum of
তাই এর
this
যে
X nucleus
decrease
is
করাটা,
0
কমে
because it is
যাওয়াটা,
at rest,
সেটা
and we
আস্তে
know
আস্তে ধীরে ধীরে
momentum
হবে।
P equal
It
to
will be a
mv, v
gradual
equal to
decay.
0 here.
If
So initially
kinetic energy of the alpha
momentum
particle
of the X
matches with the
nucleus
value of the
is
Coulomb
0.
barrier.
So after
Which
the
makes
reaction,
quite sense.
this momentum
Now,
should
if we
also be 0.
compare
The momentum distributed
the
between
wave function
alpha
for
and Y.
these two
So,
value of energies
alpha
of the
and
alpha
y
particle.
must be liberated in
Here, the
opposite
alpha
direction
particle
like this
energy is comparable with the energy of
in
the Coulomb
order
barrier.
to conserve
So the
linear
decay is
momentum.
gradual.
This is the requirement
Here
of the
the
conservation of linear
kinetic energy
momentum.
of the alpha particle is
that
quite smaller
These
than
two
the
product
Coulomb barrier.
nuclei
So the
will
fall
emit in
is
opposite
steep.
direction, and they will have opposite
So if
momentum, opposite value
we can
of the
see
momentum.
this
If
lower
Py
plot,
is the momentum of y and P alpha
this
is the
wave
momentum of the
function
alpha
psi
particle, that is the helium
will
nucleus,
be 0 at
and we
infinity.
call this
It will be very
as
small
P.
when x
Now,
increases.
Q
but
is the
still,
kinetic energy, which
the
is obviously
smallness
equal
is
to
not
half
zero.
mv square,
So there is
and
a
we know P
probability
equal
of
to mv.
finding this alpha particle,
So P square equal
whatever
to
small may be,
m square v square.
into the
If
other
we substitute
region
v square
3. So
from
we
this
still
relation,
have a chance
we will get
to
this
get the alpha particle
P alpha square by
outside
twice
region
m alpha
2.
mass of
This is the
alpha
wave function
plus
in the region
Py
2.
square, that is the momentum of y square, divided by twice mass of the
But
y nucleus.
In this case, when the energy of the alpha particles
We have
are quite
taken
high,
Py equal to P alpha
then the
equal to
probability
P.
is quite high.
So
And we can
P
get
is common, P square is common
the alpha
here, so it
particles
is
in
P
the
square
region
by
3
2
quite easily.
into
So
1 by
instead
mass of alpha plus 1
jumping
by mass of
the
y.
barrier, these alpha particles
And it will
with a
look
lower
like
value
this
of energy
after a simple algebra.
than this Coulomb barrier.
So P
This is a
square,
Coulomb barrier.
that is
This
their
the energy
momentum
of the
value,
alpha particle.
is equal to 2q m alpha my
This
divided by
is the
my
quantum
plus m
tunneling
alpha.
thing. The
And if we
alpha
want to
particle
find
will
out p,
tunnel
we just
through
need
this
to
region
make a
2
square root of
and
this
they
equation.
reach region
Now, what is
3.
the value of the kinetic energy of the
There is
alpha
an
particle?
experimental data
We have
which
already taken
shows
that
the value of
Py equal to P alpha
the
equal to
alpha,
P.
that is the helium nucleus,
That is the momentum of the alpha particle
corresponding
is
to the
designated
value
as
of their kinetic
the momentum
energy,
value
and it shows
P.
that when those alphas
So kinetic energy of the alpha particle is by
are,
definition P square
with
by
the
twice m
energy
alpha.
of 4 million
This is by the
electron
definition
volt.
of the
Their
kinetic
half-life is
energy.
10 to the power 17
And
seconds,
we have
which
just
is equal to 10 to the power 10
derived
years,
the
which
expression
is
of
almost
P
equal
square,
to the lifetime
and we
of the
put
universe.
the expression
when
for P
they
square,
are
the value of
emitting
P
with
square from
energy
here
of
to here,
10 million electron
and we
volt,
got
then their half-life
this
is 10 to
relation.
the power 7
So
seconds.
this is the amount
So
of
when they are
kinetic
emitting with a
energy
greater energy,
for alpha particles.
it is more likely to find them outside the nucleus.
Now let's take a bigger nucleus with X. The X nucleus. It's a bigger nucleus with A equal to 200, and in the n equal to n and z stability plot, we are at the high end of this stability plot. So we are taking a high value of A, and it is splitting up into two nucleus, comparatively smaller value of A. Y is with A equal to 196, alpha is with A equal to 4. So if we put the values for the masses here, we can find out the energy of the alpha particle, because this is the expression of energy for alpha particle. So for my we need to put 196, my equal to 196 and m alpha equal to 4. So it's 196 divided by 200. So kinetic energy of the alpha particle will come out to be 98% of Q. That means 98% of the kinetic energy of this fission reaction will be taken out by the alpha particle only, and only 2% will be attributed, will be given, or will be achieved by this Y nucleus.